Digital electronics play a crucial role in our technology-driven world. From smartphones and computers to advanced medical equipment, digital circuits are everywhere. These circuits process information in the form of binary digits, zeros and ones. Imagine a light switch. It can be either on, representing 1, or off, representing 0. Digital circuits use similar principles to perform complex calculations and operations. These operations form the backbone of modern computing. At the heart of these digital circuits lie fundamental building blocks known as logic gates. Logic gates take binary inputs and produce a corresponding binary output based on predefined rules. These gates, such as AND, OR, and NOT gates, enable us to manipulate binary information and perform logical operations. Adders and subtractors, the focus of this essay, are essential circuits built using these fundamental logic gates. They are the workhorses behind arithmetic operations in digital systems. Adders and subtractors are fundamental circuits in digital electronics. They perform addition and subtraction operations, respectively, on binary numbers. These circuits are crucial for various computational tasks. In computers, for instance, adders are used in arithmetic logic units, or ALUs, to perform arithmetic calculations. They are also used in memory addressing, data encryption, and signal processing. Subtractors, on the other hand, are used in applications such as digital filters, modulators, and error detection circuits. They enable us to compare digital signals, detect changes, and perform other essential operations. The importance of adders and subtractors lies in their ability to handle binary numbers efficiently. These circuits provide the foundation for complex mathematical operations in digital systems, enabling the technology we rely on every day. A half adder is the simplest type of adder circuit. It adds two single-bit binary numbers, A and B, and produces two outputs, sum, often denoted as S, and carry, or C. The sum output represents the sum of the two input bits, while the carry output represents the carryover bit. The truth table for a half adder is as follows. A BSC 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. For example, if A equals 1 and B equals 0, the sum output S would be 1, and the carry output, C, would be 0. This is because 1 plus 0 equals 1 in binary. While a half adder can add two single-bit numbers, a full adder takes it a step further by incorporating an additional input. A full adder can add three single-bit binary numbers, A, B, and a carry-in, or SIN. This carry-in input allows it to handle carryover bits from previous additions, making it suitable for multi-bit addition. The truth table for a full adder is as follows. A, B, sin, S, count. 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1. For instance, if A equals 1, B equals 0, and sin equals 1, the sum output, S, would be 0, and the carryout output, count, would be 1. This represents the binary addition 1 plus 0 plus 1 equals 10, where count represents the 1 in 10. The full adder is a fundamental building block in digital electronics, enabling complex arithmetic operations in computers and other digital systems. Section 5. Delving into half subtractors. A half subtractor is a fundamental digital circuit that performs subtraction on two single-bit binary numbers, A and B. It is one of the basic building blocks in digital electronics, often used in arithmetic logic units and other computational circuits. It produces two outputs, difference or D and borrow or B. These outputs are crucial for understanding how binary subtraction works at a fundamental level. The difference output represents the difference between A and B, while the borrow output indicates if a borrow was needed during subtraction. This is essential for cascading subtractors in more complex circuits. The truth table for a half subtractor is as follows. It provides a clear and concise way to understand the behavior of the circuit under all possible input conditions. A is 0, B is 0, D is 0, B is 0. This means no difference and no borrow. A is 0, B is 1, D is 1, B is 1. Here, a borrow is required because 0 minus 1 is not possible without borrowing. A is 1, B is 0, D is 1, B is 0. This indicates a straightforward subtraction with no borrow needed. A is 1, B is 1, D is 0, B is 0. This shows that when both inputs are the same, the difference is 0, and no borrow is needed. For example, if A is 0 and B is 1, the difference output D would be 1, and the borrow output B would be 1. This scenario is common in binary subtraction and highlights the importance of the borrow bit. This is because 0 minus 1 requires a borrow from a higher significant bit in binary subtraction. Understanding this process is crucial for designing more complex arithmetic circuits. Section 6. Understanding full subtractors. Similar to full adders, full subtractors extend the capabilities of their half counterparts. A full subtractor can subtract 3 single-bit binary numbers, A, B, and a borrow-in, bin. This allows it to handle borrows from previous subtractions in multi-bit operations. The truth table for a full subtractor is as follows. A B bin D bout 0 0 0 0 0 0 0 1 1 1 0 1 0 1 1 0 1 1 0 1 1 0 0 1 0 1 0 1 0 0 1 1 0 0 0 1 1 1 1 1. For instance, if A equals 0, B equals 1, and bin equals 1, the difference output, D, would be 0, and the borrow out output, bout, would be 1. This indicates a borrow was needed from the next higher significant bit. Section 7. Practical applications of adders and subtractors. Adders and subtractors are essential in many digital systems. They are the building blocks for arithmetic logic units, or ALUs, in processors, enabling computers to perform essential mathematical calculations. These circuits are also used in memory addressing, allowing computers to access specific locations in memory. Adders are crucial in graphics processing units, or GPUs, for tasks like calculating pixel positions and rendering images. In digital signal processing, subtractors play a vital role in tasks like filtering and modulation. They enable us to manipulate digital signals, remove noise, and extract meaningful information. Furthermore, adders and subtractors are used in error detection and correction mechanisms, ensuring data integrity in communication systems. Section 8. Solved problems, illuminating concepts. In this section, we will delve into the fascinating world of digital electronics by solving some fundamental problems. These problems will help us understand the basic building blocks of digital circuits. Problem 1. Half adder. What are the sum, S, and carry, C, outputs of a half adder when the inputs are A equals 1 and B equals 1? The half adder is a simple combinational circuit that performs the addition of 2 single-bit binary numbers. It has 2 inputs, A and B, and 2 outputs, sum, S, and carry, C. Solution. Referring to the half adder truth table, when A equals 1 and B equals 1, the sum S output is 0, and the carry C output is 1. This is because the binary addition of 1 and 1 results in a sum of 0 with a carry of 1. Problem 2. Full adder. Determine the sum S and carry out count outputs of a full adder when A equals 0, B equals 1, and sin equals 1. The full adder is an extension of the half adder and can add 3 single-bit binary numbers, including a carry input. Solution from the full adder truth table: when A equals 0, B equals 1, and sin equals 1, the sum S output is 0, and the carryout qt output is 1. This is because the binary addition of 0, 1, and 1 results in a sum of 0 with a carryout of 1. Problem 3. Half subtractor. Find the difference, D, and borrow B outputs of a half subtractor when A equals 1 and B equals 0. The half subtractor is a combinational circuit that performs the subtraction of 2 single-bit binary numbers. Solution. Looking at the half subtractor truth table, when A equals 1 and B equals 0, the difference D output is 1, and the borrow B output is 0. This is because the binary subtraction of 1 and 0 results in a difference of 1 with no borrow. Problem 4. Full subtractor. What are the difference, D, and borrow out bout outputs of a full subtractor when A equals 1, B equals 1, and bin equals 1? The full subtractor is an extension of the half subtractor and can subtract 3 single-bit binary numbers, including a borrow input. Solution. Referring to the full subtractor truth table, when A equals 1, B equals 1, and bin equals 1, the difference, D, output is 1, and the borrow out bout output is 1. This is because the binary subtraction of 1, 1, and 1 results in a difference of 1, with a borrow out of 1. Understanding these basic concepts is crucial for anyone looking to master digital electronics. Section 9. Conclusion. Summarizing key takeaways. Adders and subtractors are fundamental circuits in digital electronics, forming the backbone of arithmetic operations in countless applications. From simple calculators to complex computers, these circuits enable us to perform numerical computations efficiently. Half adders and subtractors handle single-bit operations, while their full counterparts extend the functionality to multiple bits by incorporating carry-in and borrow-in inputs. Understanding the truth tables and logic diagrams of these circuits is crucial for designing and analyzing digital systems. As we rely more and more on digital technology, the importance of adders and subtractors will only continue to grow. These circuits are the unsung heroes of the digital world, quietly performing essential calculations that power our modern lives.